Welcome to the demonstration of the software code. So the software was prepared in the Arduino IDE environment. The coding is an approximation of C code. So this is our whole software control code, as you can see here. I'll break it down into its component parts. And I'll also describe why that little bit of error you saw in the demo happened based on our control code. So the first part you can see here is just the inclusion of libraries which contain pre-programmed codes for use in our script. And the hardware, we have to define the hardware inputs and outputs to our Arduino controller, which you saw in the hardware demonstration video. So these two are the inputs for the display, which is defined here. And this is defining the servo motor. This is the analog input pin to our Arduino from our input sensor, and it goes into the Arduino's analog to digital converter, which it converts it into a digital signal for processing. And these are the hardware pins for the H-bridge controller, so it controls the direction of the DC motor. And finally, the servo motor is attached to the 8th digital pin here, which is the wire you could see in the video. So the control code essentially has two parts. It's the setup here and all these initiated variables. And then there's the main part, which is the loop part, which continues looping through. So this is just a delay we added for setup and to simulate the system shouldn't be sampling constantly. So for our demonstration we had a 25-second delay, but in real life it would be about an hour to 30 minutes because you wouldn't want your solar panels to be moving constantly. And as you can see, our loop code is actually quite short because we keep most of our coding in functions, which I will describe shortly. So essentially what our loop does, first it scans with the scan function, then it finds the maximum position. This is our input, and our input sensor goes to the max position. And then finally we have a function to move our output panel. So just to describe the scan function, it scans through the 126-degree range of motion that I had described, and it stores the readings at discrete time intervals or at discrete positions into a variable array to be compared later to find the maximum. So in our system we use 7 degrees, so it'll sample every 7 degrees. And now if we go to the section of code which finds the max here, this is the function here that does it. Find max. It just scans through the stored array from the scanning function and it finds the maximum output. And within the scanning function, I forgot to mention, we also have a section of code that writes to the display, which you could see in our demo. And finally, the output moving code, which was actually the most complicated part of our code. As you can see here, it is. So our code had to account for several cases based on the initial position of the shaft and the position where it was trying to go. So obviously if the new position angle was greater than the old one, then the shaft would have to move down, and vice versa for moving up. And our control code was pretty basic design. It was based on timing, so the amount of time that the H-bridge would allow for the motor to be on, that would determine the distance that it would travel and therefore the position it would achieve. So as you can imagine, there's a little bit of error associated with this, which you could see in our video, but as the arm travels back, the error seems to dampen out, so we didn't expect it to be too great of a issue. And we actually ran a short, small MATLAB simulation, which can actually show another reason why this error occurred. So this graph you can see here, it shows the degrees that the panel traveled versus the vertical distance of the linear actuator shaft. So the blue curve is based on the mathematical derivation of the position we did based on, the geometry of the situation. And as you can see, the blue curve isn't perfectly linear, but we approximated it linearly. So that's another source of error. And the way we did that is that we had another script here, this script here. And we just approximated it as a linear movement, so constant time would result in a constant angle difference. And then we exported those assumptions to, as you can see down here, these are the timing differences. So based on the difference of the angle, so from the previous position angle to the new position angle, there would be a time delay associated, which the DC motor would have to be on. So that created a linear relationship, but as you could see from our mathematical model, the relationship isn't perfectly linear, so there is some error associated with that. So that's essentially all our control code. Thank you for watching our demonstration.